Everyone, welcome to Unit 7, Part 3. This is our last part of Unit 7. We're going to talk about sound today, and we're going to do a little recap on the other things that we've talked about prior to this. Go ahead and read the bell work questions and think to yourself for a moment what you think the answers could be. Go ahead and pause your video. Hopefully for number 1, you explain the difference between mechanical waves and electromagnetic waves as basically their means of travel. So a mechanical wave must have a medium to travel through. So that could be air, it could be a solid, it could be a liquid, but it needs to have some sort of medium to travel through. Electromagnetic waves, those do not require a medium to travel through. So those are different in meaning like, your example could be light here. You have your whole spectrum of electromagnetic waves, and they don't require a medium to travel through. How are they the same? They're both waves. They both carry energy. Hopefully you said something to that effect. Number 2, why do you think the marchers at the end of a long parade following the band are frequently out of step with the marchers closer to the band? Well, the marchers at the end of the parade, because sound takes some time to travel, and it travels a little bit slower through air than it does through other mediums, they're hearing the music at a different time. So they might be in step with the music, but they're actually out of step with the marchers at the beginning who are hearing the music a little bit sooner. So let's go ahead. We're going to continue talking about sound. Just as a quick review, sound we know is a type of wave, and it is longitudinal. So longitudinal disturbances, remember those move parallel to the wave direction, or the direction of the wave's travel, the direction that the wave is traveling. So your longitudinal disturbances, I put a tuning fork down here. Basically, if you strike this tuning fork, it starts to vibrate, and it's basically vibrating and it's pushing out against the particles in the air. When it pushes out against the particles, it kind of smudges those particles together in little compressions, and then those compressions of particles get sent out in a wave. Okay, and they go out in all directions, but basically because we have this little compression here and then it's moving parallel to the direction of the wave's travel, that is a longitudinal wave. And basically it's just a series of compressions and then rarefactions, which would be the decompression of those particles. Okay, also, sound is basically, just like we said here with the tuning fork, a collision with the air particles. Your pressure variations are transmitted through matter. Okay, so sound can travel through any sort of medium there. And then sound waves move through the air because obviously the vibrating source produces some sort of regular variations or oscillations within air pressure and causes those particles to move out as a sound wave. Just as a quick review of frequency, frequency and wavelength, your frequency obviously is the number of oscillations per second. So we talked about this in the previous unit, or previous part of the unit. The wavelength then is the distance between successive regions, high or low pressure, when we're talking particularly about sound. Because the air particles then are moving parallel to the direction of motion, once again, this is a longitudinal wave. Your speed of sound, this is something slightly new. Your speed of sound is basically dependent upon the medium at which it's traveling through. So in the Bill Nye video, you watch that sound travels faster through solids versus through air or gases. Your speed of sound is basically dependent upon temperature if we're talking about air. So this right here is a formula. You're going to want to go ahead and write that down. Basically, you take this general, or we're going to talk about this as like a starting number, or for those of you mathematical, this is like a coefficient almost, or basically it's a leading term. It's like an initial value, okay? So this 331 meters per second is like your initial velocity for air, and then it varies by the temperature. So basically, the speed increases by about 0.6 meters per second for each degree that the temperature is either increased or decreased. So your speed of sound is greater in solids and liquids than it is in gases. We know that. But remember, unlike an electromagnetic wave, this sound cannot travel in a vacuum. There's no particles to collide. So let's go ahead and practice with this. So we knew our formula was 331 meters per second plus 0.6 meters per second times your degree in temperature. So If we look here, it says, what is the velocity of sound in the air if the air temperature is 50 degrees Celsius? So for us, we would go ahead and say our velocity of sound is equal to 331 meters per second plus 0.6 times this 50-degree temperature. And then we're going to go ahead and put that into our calculators to get our velocity of sound. You should get 361 meters per second. That would be your answer in three significant digits. And remember, velocity is a vector, so it should have a direction. For number 2, this time we're finding the actual air temperature if the velocity of sound is 319 meters per second. So we know that we're going to get 319 as our answer, and we're going to set it equal to our formula that allows us to calculate the velocity of sound. And then we're going to solve for, we're going to solve for our degrees Celsius for our temperature. So first of all, remember, this is multiplication right here, so we have to take care of that last. So we're going to go ahead and subtract this 331 from both sides. You should get a negative 12 meters per second equals 0.6 meters per second all times your temperature. And then we're going to go ahead and divide. We divide by 0.6 on both sides. I'm going to come over here. Our temperature in degrees Celsius should be negative 20.0 degrees Celsius. So that would be a very cold day for those of you from the north. Maybe you've experienced that. There's currently some snow going on up north if we're paying attention to our weather patterns. Pretty crazy. So moving on. All right, let's talk about the sonic spectrum. So this is something slightly new, but your sonic spectrum is basically a spectrum of sound frequencies that the human ear actually responds to. Hopefully you're able to test your hearing a bit with your lab that you did, and you can kind of get a better understanding of the different frequencies of sound that our ears are sensitive to. So a typical range of frequencies is from 20 hertz to 20,000 hertz, and you should have read a little bit about hertz in your lab. So obviously humans are different, and all humans hear things differently. There's actually a study that says that women hear higher frequencies better than men. They think it's due to over time women being I guess prone to listening for babies crying, which is typically a higher pitch sound. Just a little fun fact there. Obviously it's not true for all women and men, but it is something that they've studied. Just another little thing here. Okay, most people cannot hear sounds with frequencies below 20 hertz, obviously, or above 16,000 hertz. That's basically kind of your spectrum max in min. Those would also be called like your thresholds of hearing. There's particular ways you can calculate the intensity of a sound. We're not going to go too much into that, but those are all based off of your threshold of hearing. Other people are less sensitive to different frequencies, and then by the age of 70 or the older you get, you typically become less sensitive to specific frequencies also. Hopefully over here in a little joke, you guys remember what an MP3 player is. I don't know if that's too new for you or too old for you or not. Just a little interpretation of sound. Obviously, we all have ears, okay? Obviously, our ears work differently, but here's just the basic of how your ear works. So it receives some sort of pressure wave. We can start right here. And then it converts it into some sort of electrical impulses. That becomes sound waves entering your auditory canal. The vibrations of, there's like membranes and tiny bones and all kinds of things in your ear. And those vibrations obviously vibrate a little bit of fluid in our ear. And then there's hairs and tiny hairs and all kinds of stuff within that fluid that then lets our brain lets our nerve cells become stimulated, and then our brain interprets that as a sound. Obviously, we all interpret sounds differently, okay? Well, some of us are more sensitive to specific sounds, and we might hear things differently than other people. When we perceive sound, our first thing that we perceive is pitch. So high pitch, low pitch. Your pitch, hopefully you guys are now relating to your frequency. So your frequency and wavelength are two physical characteristics of sound waves. That's a little bit of review. But your high-pitched sound should have a higher frequency. Low-pitched sounds would have a lower frequency. Your then amplitude is what you perceive as loudness. So depending on how loud the sound is, that's based off the amplitude. And that's kind of how high that wave is disturbed from its equilibrium point. So remember, frequency determines pitch, amplitude determines loudness. You guys might have heard of something called the sonic boom. We're going to go over quickly just kind of what that is. So just imagine, this is our little example here. We have a water bug. He's swimming in the water, and we're going to use water because you guys can visually see the ripples moving away from an object that's in water. If you drop a pebble or a stone into some water, you can see the ripples move away. So imagine that little bug. Here he is. He's swimming away, and as he's swimming in this direction, he's pushing and pushing and pushing against those ripples or those waves because he's then compressing them. The waves are moving out in that direction, and he's also moving in that direction, so he's compressing. Over here, the waves are a little bit more decompressed because it's simply just the waves that are coming out from his motion. The bug's not actually moving in that direction. So if your yellow lines represent the wave crests, then your bug is actually bunching up the wave crests here. So down here, if you look, it says that the velocity of the bug is less than the velocity of the waves. Let's go ahead and imagine that the velocity of the bug is now equal to the velocity of the waves that he's producing. So once that becomes equivalent, then that means that the bug is actually moving as fast as the waves are. So out here, we're creating a little bit of barrier. There's a barrier of the bug's motion and a barrier of the waves, and we're going to talk about this barrier as a wave crest. Okay, in this particular example, it would be a water barrier. Okay, but watch what happens next. The bug is going to break the barrier. So imagine the velocity of our water bug swimming on top of the water now becomes greater than the velocity of the waves. If he then breaks that barrier, it's going to fly through there, fly through that barrier, and then each crest of the wave then now is behind the bug. So the wake following the bug is produced by an infinite amount of circular waves that are then superpositioned one over the other. This is how a sonic boom occurs, but with sound waves. So if you think about a sonic boom, we have, you guys might think of like fighter jets. That's probably the most common thing that you can see breaking the sound barrier, that you might have maybe watched a video on. But basically the same thing happens. This plane is flying out farther and farther and farther, and it's compressing. This plane is actually making noise, traveling in this direction. It's compressing and compressing and compressing and compressing all of these waves, and then it eventually breaks through that barrier, and then that's when you hear the sonic boom. All right, that's it. That's all I got for you. So your homework for today is to go ahead and complete the Unit 7 test review. This was just a quick recap of sound and some of the other things you've learned. Your test review covers Unit 7, Part 1, 2, and 3. Make sure you show all your work, upload your notes, and then obviously the answer key will be posted before you guys have your assessment next week. I hope you have a productive day.